This is about where we left off last time, right? We started making our own linked binary search tree. It's generic, but there is a restriction on the type. The types themselves must have some ordering. Otherwise, the whole point of this linked binary search tree is that it's got some, it's following that ordering. If the elements themselves don't have an ordering, then what are we doing? So the elements have to have an ordering. Two fields, int size, a reference to the root, because if we have access to the root, we have access to everything. Because we're saving the size, those example methods we looked before that would go and count the size of the tree, we don't need those. We'll just keep track of the size. Every time we add something, we increase it. Every time we remove something, decrease it. That's all. Linked binary search tree. From the constructor, it starts empty. Makes sense. And we're using a static inner class that's just data with left and right nodes and some accessors and mutators. That's all. So that's where we are. We're just starting, okay? The node class, fairly straightforward. We have two constructors here. One that just calls, it chains. It calls this one with null in it, so data becomes null and the rest are null. Otherwise, we could specify the data where we create a node with some specific data in it. It's handy. Two constructors. Do we need to? No, we could set the data, whatever, it's fine, but I did it this way. Cool? Any questions at this stage before we carry on? Okay, so adding to the binary search tree. We're going to be making use of a lot of recursive methods here, just because the methods are so much nicer and cleaner recursive. There are a couple I do iteratively to show a comparison, but I like the recursive ones. And often, a lot of these recursive methods start with this public-facing non-recursive one that calls a private recursive one, just to set up. It's that, going back to that idea of doing a linear search, where the recursive one, it takes some arbitrary index, but when you start it, you always want to start at index 0, so we just have a method that automatically calls the recursive ones with the starting position. So public Boolean add, it takes an element we want to add. How do we add it? Well, remember, a binary search tree has a very specific set of rules. When you add something, it must go where it belongs. Given any tree, when you add something, there is a correct spot for that element, given the state of the tree. So where is it? You just do a binary search as if you were looking for that element. And I mean, if you find that element, if we allow duplicates, which we will, we'll just go to the left. But find to where it would go, and then replace that null leaf where it should be with the thing. So how does it look? Okay, add, this weird thing about root, you'll see in a moment why we're doing it this way. Add takes an element and the node we want to check to add it to. We're going to start at the root. We call it on the root, but this add apparently returns the root. You'll see. Increase size, return true. Why increase size? Well, as soon as you add something, we got to increase size. The recursive method's not going to do that. Return true because it should return true. This might not make as much sense until we look at the recursive add. So what are we doing here? Private, this time it returns a node of type T, not a Boolean. It returns a node of type T. Add the element and the node current. Okay? So, what we do, if current is in fact null, so imagine the starting case where null, the root of the whole tree is null, right? Well, it would go there, right? So if current is null, meaning, okay, the node we're looking at actually doesn't exist, we'll put the element there, okay? So what do? We return a new node, okay? Now this might be a little weird, but hang in with me, right? It is a little funny, but hang in. Otherwise, compared to the element, if the current is actually greater than, if the element I want to add is actually less than current, I want to go to the left. But notice what I'm doing here. I am saying current sets your left to the result of calling the recursive add. Okay? Okay? So, let's try to think of this in a couple of stages, okay? Let's say this is root. Root is null, okay? I call it, current is, here. Current is null, this is root. R for root. Call add, go down here. Current root is null. If it's null, return a new node. Oh, okay, so make a new node with, well, x, whatever I put in there. And return a reference to this thing. Root is now updated to the reference to that thing that this just created and returned. Okay? Now, imagine we have a case where, like, the left is null. Can you see this clearly? Imagine we have the case where left is null. All right? So I go, okay, root, which is also current. I say, okay, if the element I want to add actually belongs down here, and this is null, which it doesn't have to be, but let's pretend it is, I'm going to say, hey, current, set your left to the result of calling add on the left. Okay? So if that were to happen, the next go through, current would be here. We make a new node, we put x in it, and then we return a reference to, perfect, right? It returns a reference to the node, the left gets set to the reference that was just set. Cool? Cool. Similarly for the right. Now I know what you're thinking. You're thinking like, well, what if it's not null, right? You're creating a new node, but like what if the current in that case isn't null? And then immediately I go down here and I'm saying, okay, set your left to calling it on the left, but that wouldn't return a new node. No, it wouldn't return a new node. If you look down here, it returns current. It returns a reference back to current. So if we go down here, this is current. And who cares? We go down here and it gets added somewhere down here. But like, let's go back up to the top where this is root. And this is not current anymore. Okay? Here I said set your left to calling add on the left. If it doesn't return a new node, it returns current, which is itself. So we just reassign it back to itself. Entirely fine. I'm not going to lie, this ain't trivial, but it's nice. It really is nice. And if you don't see that it's nice, see that it's nice. You bet I love stuff like this. Yeah.
And does it always also add a null node?
It'll never add a null node unless, no, it never adds a null node. Think about your question just a second longer and then ask it again. Any other questions? Yeah. Speak up, speak up. Well, it'll never add a null node because if it ever gets to a null node in the tree, it replaces the null with the new node, right? So if I just called set left to add, we go down here and now current, because current is the left in that case, current would be the left node. If the left node was actually non-existent, you make a new node, we return that new node, and suddenly the current, you go back a level up that call stack to the previous call of the recursive method. The left set left is actually now that new node. Or if we call it on the left, and the left isn't null, it still exists, and it goes down and whatever. It adds somewhere, and we keep returning, and eventually we get to that call where we just said, okay, current.setLeft, call add on your left, right? And we go in there, and that node actually exists, and it's not null. Well, that's fine, because down here we're returning current, so we return itself, meaning that we say, hey, current, set your left to itself. That's what would happen in that case, right? This idea of like setting the left, setting a reference back to itself is a common strategy in recursion, by the way, in a situation like this. This isn't uncommon, this is typical. Do you have a follow-up question?
No, I think I get it, but I want to see more examples of this.
More examples? Well, have fun. We can say, Here, let's do an example. You know what? Maybe let's see if I have an example. No, I don't. Okay, so let's say we have 10, 5, 3, 5, 4, 100. Who cares? Let's say we want to add the number 6. Okay? Okay. We start with root. Okay? I want to add the number 6. So I call it here where element is 6. Okay? First of all, we know that the 6 should go here. Why? Well, because it's less than, greater than, it should go there. Okay? Okay? So, we go down here. We are now on the recursive call 1, let's call it. And here, current 1 will be that node. Okay? And I say, hey, are you null? No. Okay? Is the current's data greater than the thing I want to? Yeah, okay. So I want to go to the left. Okay? So I say, update your left to be question mark. Okay? I'm updating its left to be something. But I'm calling another recursive call, R2, and now C2. On that second recursive call, there's another current reference variable. I'm calling it C2 here for current 2. This is current 1 because it corresponds to that recursive call. This recursive call is not done yet, right? Because it's called another add right here, and it's waiting to continue as soon as this is done. As soon as this is done, it can continue. All right? So C2. Is C2 null? No. Okay. So where does it go? Well, it goes to the right. So we're going to update this current 2's right to be, we don't know. Okay? R3. Okay, this is C3. Is C3 null? No. Okay. So should it go to the right? Left? No. Right? Okay. Another recursive call. R4. And we say, okay, call it on this node's right. So, and then update its right to C4 is null. Okay? So we had 1, 2, 3, 4. That fourth recursive call. We're there. So far, so good. Any questions? Happy, sad? Any questions? All right, so we're there. And we say, hey, current, are you null? Yep. So what do? Create a new node with 6 in it, and then return a reference to that new node. So return a reference to this. Oh, wait, this was a big question mark, right? So we go back. C3's right node is now set to the thing that just got returned, which was C4. Okay, this is now done. We return to C2. C2's right is set to what this one returns, which is current. C3 in this case. So assign it back to what it was. Okay? C3 is a reference to this node. This node's right is that node. But we're saying update it to be whatever C3 references, which is what it's already referencing. The magic only happened when we actually created a new node. Every other one just reassigned it back to itself. Up to there, this one's left gets reassigned back to what C2 references, which is a reference to what it's already referencing, so it just goes back towards itself. And then here, we return current, the root node return current, which is the root, which gets reassigned back to the root. The root gets reassigned back to the root. Every call to add will return the recursive one. Every call to add will return current unless current is null. That's it. That's like the magic there. Get used to patterns like this, of like having it reassigned to itself. That's a common thing. Did that example help, do you think? Cool. If it didn't, do it again. You can do this. Remember, there's no trick other than what does the code say. If you don't know, do an example. Yeah, but how am I what does the code say? You can't use that excuse anymore. You can't have come this far and have the ability to say, but I don't understand what the code says. What are you talking about? Yes, you do. You can't have gotten here and not be able to follow that code. That doesn't mean it should be easy for you. All I mean is you definitely can work through it. What does the code say? That's the one trick. Minimum and maximum. So any other questions about that add? Okay, let's find the minimum maximum. Well, min I'm doing recursively. I do find the min if it's empty. Is empty. We haven't written that method yet, but I'm guessing you can figure it out. Just return size is 0 or not 0. If it's empty, empty tree, whatever, exception. Otherwise, call min on the root. So min here takes no argument. The recursive one, presumably, the private recursive one takes a reference to a node. And what does that do? It's pretty straightforward. It's basically a linear search until you find the end. Get left is null. We found the min. Otherwise, call min on the currents left. Go all the way down the tree until its left is null. Cool? Max, here I'm doing it iteratively. Max if it's empty. Otherwise, current is root. Well, current get right is not null. Current equals currents get right. And then we get done, get the data, whatever. Same algorithm, recursive, iterative, whatever. Due to the ordered nature of the binary search tree, go all the way to left, right, whatever. Cool. This is done for demonstration purposes. Oh yeah, the minimum functionality is implemented recursively, maximum implement iteratively. If you're like, why is one iterative and one's recursive? Just because I wanted to show you that you can do it either way. There's no advantage. Oh, it makes more sense to do maximum iteratively because, no, that's nonsense. It's just strictly to just show you the comparison. That's all. Okay? Remove min, remove max. All right, well, remove minimum. I've got a public and I've got a private. What's going on here? These are going to start to get a little hairy, so make sure you're paying attention. Remove min. T, return element is null. So we start with this variable that's just nothing, whatever. Okay? If it's empty, no such element. Otherwise, if roots get left is null, meaning, what if the root is the minimum node in the tree? Right? It's entirely possible that our tree, let's do the opposite for ease here. It's entirely possible that the root is the maximum. Our tree could look like this, right? And in this case, 10 is the biggest number. Similarly for minimum, right? So if it's the case, you'll notice that this public-facing one has to do a little extra heavy lifting for like bounds and edge cases. If roots left is null, return element is the root's data. So get the data out of the root because it's the minimum number. And then root is just going to be now the root's right. I'm basically removing the root. But we still need a root, so we do that updating. Otherwise, we call return element on remove min root and get left. Because if the root's left does exist, go to the left until you find it. After all that, reduce size, return the return element, the minimum number. You'll notice that this method does return the data, the minimum value from the tree. Yeah?
When you call remove min,
Here, there are none.
yeah, but like when you call it else.
Looks like there's two. Parent and current. And this is, never be afraid. Like, a lot of people try to get fancy. You could add as many parameters to these as you need to make it work. Now, obviously, if you're writing a recursive method that requires like 17 parameters, I don't know. Maybe don't. But here, we're always going to have reference to the parent and the current node. So presumably, in a case like this, like I could have like current is the one I'm currently like investigating, and parent would be current's parent. And this might be helpful for various cases because let's consider, like I have a 4 here. That doesn't make sense. Who let me do that?
All of us,
All of you.
including yourself.
Yeah, I was testing you, totally. That was a mistake. I had a 4 over here. That was wrong. Why? Because 4 is less than 5, so it shouldn't have been. I know, it shouldn't have gone there. Yeah.
Oops. To be fair, I didn't see it.
To be fair, you didn't see it? Okay, you've got the one excuse. Anyways, let's say we had something like this. If I want to remove, if I didn't have reference to a parent, I'm in a bit of a pickle because I want to remove this 3. But this poor little 4 has to go somewhere. Where? It's got to go like up here. So I need to actually update current parent's left child. So I need access to the parent in order to update its left child, right? You could do this kind of another way too, where you have current and, like instead of having like current and parent, you could have current and like left child and kind of like do it in another way. It's entirely fine. I'm just doing it this way. Yeah?
How would it work if the current is the root?
If the current is the root, we just did that. Remember, like I could have a tree like this. 10, 50, 40, 60, 55, 45. And I say remove min, right? There's kind of an easy solution. You just, okay, that's now the new root, right? And that's what we were doing right here. If root's left is null, that means root is the minimum. And if you're like, why? Well, if its left wasn't null, that means something is there. And if something is there, it must be less than the root. Okay. So what do we say? We say, okay, if current's left is null, parent's left is current's right. Now, but what if like current's right is null? Well, then who cares? Its left will get set to null. Whether this exists or not doesn't matter. Whatever it is, parent's left must be whatever this is. If it's a node, great. It must be that node. If it's null, great. Null. Yeah?
And that one, the right node still has reference to its ones if it has one under it.
Yes, this here, whatever it is, would have whatever these are. It's entirely fine. Yep. So if it exists, then there. Everyone's happy. And maybe this node that it gets replaced with is not necessarily the new minimum in the tree, because it could have left children. Right? Like if I have a case of like 7, 4, 6, 5, right? If 7 goes down to here and we remove the 4, left, 5 is the new minimum, right? So be aware of that. That's important. Okay. Oh yeah, this removes, okay, the t. Parent dot set left, currents get its right. If it's null, we set the parent's left to null. If it's not null, we set it to whatever it is. And then return currents data. Otherwise, call remove min on the left, right? Again, basically currents left if it is null, you do all that. If it's not, just keep going to the left, in the same way that you would do the recursive search down to the left. Good? Good. Now, what about remove max? Well, here I'm doing it iteratively instead of recursively. Again, why? No other reason than just to show you. You'll see this is kind of a mishmash of the previous stuff. return element. If it's empty, whatever. If the root's right is null, we found it, just update the root. Otherwise, here I'm just going to use two reference variables I'm going to create where the parent starts at the root, current starts at root's right, and then we just go like down the tree until we find it. And then it's the same logic, right? Well, current's right, because if we got to this point where current's right is not null, well, now we know current's right, or sorry, if parent's right is not null, root's right current must not be null, because we just checked that it isn't null. So then we can immediately start by saying like, hey, current, is your right null? If it is not null, you keep looping. That's what this is. So this loop is like keep looping until you get to the point where current's right is null, until we find the bottom. Then what do? Return element is current's data. Parent.setRight is current's get left. Size minus minus return element. Cool? Cool. Any questions, thoughts, concerns, anything at all? Yeah.
These can be like swapped. This like the remove min would look very similar to this.
If we made it iterative, like with a loop, absolutely. We would just flip the lefts and the rights. That's basically it. And this would look recursively the same. You just flip the left and the rights. Man, it's warm in here, eh? Wow. Whew. Whew.
You're telling me I have a whole lot of food on.
To take it off? No. Oh, okay. Just checking. See, I don't even know if the thermostats in these rooms really work. But what does it say it is at least? It says it's 23, but I don't know. I wouldn't be surprised if it's.
Yeah, I feel like it's 26.
I honestly think they could bother to invest in some dehumidifiers or something.
Whew. I don't know if it's moist in here, but it's warm at least. All right. Cool. Other questions about this? All right, there's remove min, remove max. Okay. Now, what about a general remove? Okay. This is probably the trickiest thing we're going to do all semester. Okay? This part right here. It really isn't too bad, but it requires a lot of connecting the dots here. All right? So, I've got this, okay. Oh, there we go. This is probably the most complex functionality discussed this course. To help, we're going to break it up. So, we've got this remove. It's a public-facing remove. Let's start with that, okay? If the element isn't, we've got this contains method. We already looked at this. This is the binary search, okay? We talked about this a few topics ago. If the element's not there, just return false. We can't remove it, whatever, easy peasy. Otherwise, do a comparison to check, okay, is the thing I want to remove to the left or to the right? Okay, that's what we're getting the comparison. If the comparison is 0, well, I'm going to replace the root. Basically, if I'm starting at the root and the root is the thing I want to remove, remember, comparison will be 0. Doing this compare to returns 0 if the elements are the same. So if the root's data and the thing I want to remove are the same, I found it. I want to remove it. So do the root, and then I've got this helper method here. Find replacement node for the root. More on that shortly. Else if comparison is greater than 0, we'll remove on the left, otherwise on the right. So this is a recursive version right here. These are the recursive ones. So we have the public-facing one, and then these we'll call the recursive ones. Start doing a remove on the left or the right. And then when you're done, size minus minus, return true. Assuming that we were able to remove it correctly, that's what we're doing there. Okay? Now we have two things to investigate. Find replacement node and these recursive removes. For now, find replacement node is this beautiful, wonderful, magic method that will give us the node that, like if I want to remove a node, okay? Like if I have the tree right here, 50, I want to remove 50, it's going to give me the node that I need to like put back here. Because if I remove 50, I got a problem. I got all this subtree and these subtrees that need to be dealt with. So if I want to remove 50, I need something to put in its place, right? We talked about this. How could we do it? You might remember, go find the smallest number in the right subtree or the biggest number in the left subtree, right? Why will that work? Well, the smallest number in the right subtree would be, first of all, it's possible. Remember that it's possible that duplicates are down here, right? But this, we don't need to have this discussion whether there's duplicates or not. We can assume there's no duplicates allowed. Fine. Everything over here is bigger than this number. The smallest number in this tree, in this right subtree, of all the numbers bigger than this, the smallest number bigger than this must be the leftmost node in this subtree. So the smallest number that's bigger than this in all of this must be the leftmost subtree of this, right? Similarly for over here. The biggest number, the number that is less than 50 but bigger than everything else in this subtree, therefore safe to put here, would be like this node, right? Do you remember why I picked to go to the right? Because it could have duplicates, and wouldn't it be nice if, the tree actually kind of stayed exactly the same, That then begs the question, is that necessarily better? No. Yes, I don't know. I like it, and that's why I did it. If you want to make an argument that it's not nicer, then fine, fair enough. I had a choice to make, and I needed a tiebreaker. My tiebreaker was like, well, it could make the tree kind of like unchanged in a nice way. Unchanged in the sense that the value didn't get removed from that spot, but anyways. Because with remove, it's not about removing all of the values that are equal. It's about removing an instance of the value that's equal.
You don't care which.
Yeah, you don't care which one. All right, cool. So before we and that's the idea of this beautiful little magic method here finds me the value, like the node that I can like put back in there, okay? Okay. But it's not as simple, by the way, of like, it's not as simple.
What? Is it 50?
That's a 56.
Oh, okay. Bad one.
No. That's on you. No, look at that. Is this better?
Yeah.
Is it?
It's evil, but it's clearer.
No, you could have erased the numbers and brought them again.
No. The eraser's all the way over there. That's not possible. I'm not getting my hands dirty. So, I can't just say like 55. It's not as simple as just putting like a 55 there because, well, what about this little guy? What do I do? How do I? It could be complicated. But for now, briefly, we've got this beautiful method, find replacement, that just deals with it for us. So let's do the recursive one. What does the recursive one say? Okay, comparison, do the comparison. If we find it, okay, so I found what I want to do. You'll notice I've got some nested crap in here. Let's come back to this. If I find it, I got to do something. If I don't find it, I carry on to the left, I carry on to the right, depending on if it's to the left or to the right. Okay. All right, so what are we going to do here? So if I find it, and if the parent's data compared to the current's data, what is going on here? So if the parent's data compared to the current's, if the parent, we have parent and current. Okay, so what am I asking here? I'm saying if my parent's data, comparing it to the current's data, if the parent's data is bigger than the current's data, parent.setLeft, find replacement node. Otherwise, find, so this is checking. Here's what we're doing. At any given moment, this recursive one here has the element I want to remove, a parent, and a node. Okay? But the current node doesn't know if it's the parent's left or right subchild. Right? That's all this is doing. It's checking, okay, are you the left or the right subchild? Or not subchild, child. Okay? When I call it, right, like if this is parent and this is current, when I'm calling it from like this perspective, I go like, well, clearly it's the right subchild, or the right subtree, the right child. But if I just have parent current and I go like, I don't know if I'm the left or the right, so I can easily find out though, like is my value relative to the parent more or less, higher or lower? Cool? So that's all that's doing. So if the parent's data is bigger than the current, yeah, that means the parent's left has to be updated to be whatever this new magical replacement node is, right? Because that means current is what I'm removing. Okay? So I guess I could have left that as like R, P, C. Okay? So I say, hey, is the parent's data bigger than me? Yes. That means it's the parent's left node that needs to be like replaced. Right? Nod so I at least can tell myself you understand completely. Perfect. So parent, set your node, your left, to be whatever this magical method is going to do. Again, we're going to get there shortly. If it's not, that will, okay, same thing for the right. Okay? Now, of course, this method right here is doing a lot of heavy lifting. So this is just magically finding the new node to put in there, right? What do I do? Just use your eyes. Okay, the private remove is basically doing a binary search through the tree looking for the value to remove. Unlike the binary search, however, this method must remove the element, potentially address a gap in the tree if the node being removed is an internal node, and ensure the binary tree ordering is preserved. To do this, another private method called find replacement is used. Woo! A lot of comments. Now, those comments are there for you, not for me. So what are we doing here? There's a lot of explanation, but let's see if we can look at the code and work through it. So, replacement node. Find replacement. We give it a node to remove. That's the node being removed. Okay, it's a reference to the node that's getting cut. I need a replacement node that starts as null. So, if to removes left is null, you might remember we talked about the various cases. What happens if what if it's a leaf node? What if it's an internal node? What if it's the root? What if it's this? What if it's that, right? All those different cases, how to address it. Well, let's talk about them. If its left is null and its right is null, it's a leaf node. And if it's a leaf node, I'm going to replace it with nothing. Doesn't matter. Now, you could say like, oh, well, that's already not. Just shut up. It's intentionality, right? There we go. Replacement node is null. We skip all these else ifs. Return the replacement node. Yeah. All right. But what if its left is not null, but its right is null? Okay? So we have a case like right? This is like to remove. Okay? Its right is null, but its left isn't null, and who knows what's going on down there. This is the case. All right? So, if this is the case, it's actually rather simple. Just promote this guy. Right? So, replacement node is to removes left. Awesome. Right? Right? If I want to remove this one, there's nothing here, just, and we're happy. Similarly for the other way around, okay? If this doesn't exist, but this does, just, update it. It only gets hairy when they're both not null. Okay, okay, we have a case like this or something. Oh, what do we do? All right, so what are we going to do? Well, it's iterative. Okay, any questions so far? I think everything so far is actually not too bad. And I know we're not going slowly. We're not going too fast, but we're definitely not really going slowly. But I highly recommend you take your time with this. What are we going to do? We start with a parent and current. Parent is to remove. That's the node being removed. We start with the parent. Okay, whatever. It's its parent. Current. Current is like my attempt to find something to actually replace it with. So to remove, go to the right. Why are we going to the right? Because, again, we could either go to the left or to the right. But if we go to the left, we need to go to the if we go to the left, we have to go to the rightmost node. If we go to the right, we go to the leftmost node, right? We're looking for the in-order successor. That would be the next smallest element in the tree, right? So the minimum value in the right subtree. Yeah?
Can you do this recursively?
This part, probably. I mean, technically, well, there would really only be this part, and then we'd still need all this crap. It's probably just a little, yes, but I don't know if that's a good idea right now. So find the in-order successor. So to removes right child's leftmost node, the minimum value in the right subtree. Okay? That's what we want to find. How do we do it? Well, that's easy. Keep going to the left until the left's null isn't there anymore. Okay, great. Yeah?
Could you also use min?
Call the min one? Well, the only trouble there is we need reference to parent and current in here to be able to kind of do all the magic. Okay? So, I think if we follow this through with an example, it might be handy. X, Y, okay, Z, this is my situation. This is the one I want to remove. Okay? Okay? This is TR. Yeah? Here, let's So, I want to be, can you see this well? I don't care what's up here. I don't care what's over here. This is to remove. This is the node I want to remove. This exists. I don't know what's in here, but something exists. Something exists. This is the min. It may or may not have a right subtree. And over here, there may or may not be a right subtree. I don't really care. Okay? So, what do we do? It starts with parent is to remove. Current is that. Then I say, okay, current, get your left. Is it not null? Okay? P, C. Okay? No. P, C. Then we say, okay, current is your left null. Yep, we're done. So this is our state. We are right here. Okay? 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 Replacement node is current. This is just giving it a new name because it's a little nicer. Replacement node is current. Replacement node, set your left to be two removes left. Okay? This is to remove. This P is old. That's an old P. To removes left. Okay? This node here is getting promoted. So it's new left. Everything over here is less than this, which means it must be less than everything over here, meaning it must be less than this, and it's entirely fine. So we can then say you are there. So your left, the node that I want to promote, your left subtree that didn't exist, because if it did, you wouldn't have been the min value, is now this node's left subtree. Okay? Now we have, okay, now if 2 removes right is not equal to the replacement node, because it's entirely possible that like this could be the min value in the right subtree, right? Where basically, oh, the root of that subtree is the min value, right? That's entirely possible. If that's not the case, parents left is replacement nodes right. So this one here, parents left, which is getting eliminated effectively, because this guy's going up here, but its left actually goes to whatever that is. Why is that safe? Everything over here must be less than this, because it's to its left, meaning it's entirely fine. And then replacement node, your right is now 2 removes right. That better be what it says. Yes. Yeah. I went through it quickly, but you should be good. Yeah? Yeah? Happy? Sad? Yeah? Yeah.
Would X still have reference to its left?
Technically, but it's being like eliminated, right? So, yeah. And then we return the replacement node because that's the node that's actually getting put into there, which would be set to this, whatever that is in the recursive call, right? Because remember, this is returning a node that is actually being, if we go up here, like it's setting to whatever this returns. So yes, it does, but it's also being eliminated and we lose reference to that, so they just kind of disappear. Cool. It's pretty cool, right? Yeah. Now, like I said, this is probably the most complex thing that we're going to cover all semester, which means I like it. Yeah. Oh, yeah. Like, I tried to make it as pure as possible, but like this is a method that's manipulating a data structure, so it's just, it's very, it is. Yeah. Cool. Contains, there's a binary search. Yeah, cool. We'll pick up here on tomorrow?
Yeah.
Tomorrow? Yeah, cool. We have 3 activities we got to do left, right? All right.
I mean, technically, we don't have to.
I guess we do them in the syllabus.
The syllabus, yeah, I checked to say if I don't do them, do I change it? And I didn't, which means I better have the 10.
Oh, okay.
Yeah. Well, we don't have time today.
So we probably have
Three classes?
I never say I won't have more than 1 in a day.
Oh, that's true.
So
Okay, three in the lab. Let's go.
we'll find out. Don't give me ideas, yeah. Any last questions before we wrap up for right now? Yeah.
For our lab this week, it's on heaps. Are we covering like topics on?
Nope. That's for you to figure out and have fun. Heaps are fun though. Basically, it's how to make a tree in an array. That's what a heap is. It's pretty cool. Yeah. All right. You're lucky. We're ending early today.